back on the stream. All right, so the second exercise is about system fundamentals. So first three are about linearity, causality, and time shift invariance of the system. The stability we are not testing by numerical methods or the kind of simulation methods, because stability you can basically find out from the system transfer function. But before that one, actually, we have some say we need to define if or find out if the system is linear time invariant, LTI. Then we know how to actually handle that one. Out of that, you can find out the stability, and also actually causality you can also see from the zero pole plane. Okay, so let's start. The linearity was simply about the time shift. The system is additive and summative, meaning that you can apply the superposition principle. So if you have a two input signals, should I call them x1 and x2? I think I will, well, it doesn't really matter what I call them. Okay, and sum the inputs, put it inside of system under disk. So this is our system, whatever that is. It does some calculations, it has the function defined somehow. And we have the output here. And this output is A times xn plus B times yn. And the question is actually, if you take that one and run the same signals through the system separately, scale the output and sum, which is then the A times the system function xn plus B times system function yn. The question is, are these two outputs the same? And in Matlab, that actually is quite simple to test. The only small minor problem that if there was a mathematician here, anyone actually here with a mathematics degree? No one? Okay, good. Since mathematicians would disagree a lot, because this, what I'm showing here, is not explicitly true. So it's just a test, simple test that can be used to show if a system is nonlinear, but not proving exactly that the system is linear. We are using basically random numbers to test it. So pick random test vectors. We already know how to, right? And also some random values here. And fix those values, run the test this way and that way compared to outputs. Okay, so with the Matlab, I take the random test vector. Let's see, I might actually call this non-linear oops, non-linearity test. Non-linearity test. And basically, if we, for example, have a function, what should I use here? Well, well, I'll just leave it there. So, for example, function. I need just some test function here. Our test function would be, hey, is that 4-point average? Haha, 4-point running average. And actually, that would be just a very simple. The function here is actually just filter. So that's the 4-point running average. You can always do the convolution yourself, but anyways, this is the brute force kind of approach. We are actually going into this one, or is it next week or something? Or actually, we might have it even this session. I'm not sure yet. Okay, but anyways, filter is an implementation of LTI system. And okay, now basically I already know that this function is linear, but I will test it anyways. So first I need the two test vectors, for example, uniformly distributed numbers, 100 points, or random numbers, and this is a the row vector, so one single row of values there. And then another one, same thing. These are different random numbers. Then we take even this A and B as random number, but this is just one random number. B equals also a random number. Oops, there. So now those are randomly picked, which doesn't guarantee anything else than, well, we are trying this equation with two different data sets with and two different values. But anyways, it's supposed to give us 0 as a difference between those two results. And first I calculate the that system or output of system with, oops, why, oops, calculate that one. So we calculate first the sum. So our XX or input for the first one, input 1. Okay. Input 1 is just simply A times XX plus B times YY. Okay, that's the weighted input. There. Then I calculate the second. Oh, that second input is just actually those separate inputs. Input 1 is that one, and output 1 is just filter divided by 4, and then that input 1. There we go. So that's the system output for this combined input. There you go. Now next we calculate the separate outputs, so f with the value x and y with the value y, and multiply those together. So output 2. I'll do it on one line. I hope that I actually have enough room. So 8 times. I don't have enough room here. Well, I will continue. Well, I'm just mumbling here myself. Don't mind me. Okay, that's 8 times output with x plus. Okay, 3 dots actually continues. With the second line. I basically also can copy the first line, since they are almost the same. All right, so that is the output for individual weighted outputs. So no, yeah, x y. I'm not sure.
Would you mind saving that as a script?
Yes, I can.
Yes.
Or you can. Yes, and basically this command history will give you perfect scripts. I will copy that perfect script there on the workspace. So the command history is actually a script file. I have used, as I said, I'm a dinosaur. so I'm an old guy. I type things, and on the other hand, I can always take whatever I've tested first and make a script that one. So on the command history, if you basically just paint something here, then you can make create script, and that's your file. But anyways, I do it this way. And yes, you could also do this function separately as a Matlab function. Okay. If you like to do it that way, go ahead. Okay, but anyway, so output 2 is basically that one. A times the output of system with the x plus b times output of the system with y. Now we have 2 outputs. How to compare if they are different? Okay, how many of you have taken the Unix course? I think it should be compulsory. In Unix, you can compare easily if the files are the same.
Just by using
diff, yes. I think it's also here is diff, but that's my guess. I might be, mixing it with Unix, but yes, exactly, and that's what we are looking for, since these are actually vectors in space, so n-dimensional space, 100 dimensions actually now. If when the vectors are the same, and the difference is the 0. So what we are trying to calculate is the okay, that minus this one, and then the second norm of it, or norm, any norm actually will do. And we test if this one is 0 or close to 0, because of this is computer, it does errors. Whenever it does calculation, it does small errors all the time. Floating point numbers. All right, so we do that one. But I'm not sure about the diff. I think it is diff, but no, it's not the one. I would call it diff, but I could also use the say norm. Norm returns the 2 norm of or Euclidean norm of vector v. So yeah, so that's the distance or the length of the vector. Okay, we use norm. Sorry about the diff. It's actually the difference between those vectors. So calculate. Sorry about that. So it's second norm. The difference vector would be still a vector, but norm is the scalar number. Easier to compare. Hopefully this is 0. Ah, yes it is. It is 0. This is floating point precision numbers, what we are dealing with. And that's very close to the machine epsilon, which is the smallest difference between the numbers. The machine epsilon is EPS, and that basically we have 4 times the epsilon is the our difference. So it's within the calculation the limits. It's the same. Those are the same. So this is a linear system, but I knew it already. So it's the running average filter is a linear system. On the exercise, though, basically there are different kind of system outputs. I would actually, if I was you, I would go and do a separate function to test them. So. Good. That's how you check if the system is linear. Basically, the other two, the causality and the time shift invariance, go about the same way. Okay. There we need to start a vector at some point, run it through a system, and see if the output actually is 0 before the this signal start. Okay, so causal. So no output before input. So we take any signal random which starts at certain point, run it through a system, check if this one has any non-zero elements before this one starts. Okay, so it means that we had basically need to start the signal, for example, like this. So we can actually use here the step function. And then we basically check this part here. That should be 0. Actually, this is also non-causality check. Doesn't really prove the causality, but it can be used to prove the non-causality. The other way, it's just a guess. But it's, hey, this is not science. This is engineering. So it's as good as the real paper and pen math, except this is more usable. But I will call it just in case, non-causality check. So test with well, if the system remains 0 until start of the signal. There we go. And there you actually need some time shifting operations. How to do time shifting. And basically time shift of n steps same as filter. We start with the filter. Time step of 0 step would be just 1, but we actually put here zeros as many as we have these steps. 1 and n at the beginning, and then 1 here. Okay, this actually convolutes the signal with that response function. Okay, that's time shift, negative time shift. So this is delay. Positive time shift, which means advanced operation. So plus m. You need to first reverse order the this data, and then actually do time shift and then reverse order it again. I don't remember the name of the function. It might be reverse, but we can take a look at reverse shift minus n and then again reverse. That's the easiest way of doing positive time shift. You might actually need that one also on the calculations. But anyway, since we already have that x, that's just fine. That starts somewhere. But let's see. I will make it more interesting by making indexes from minus 49 to, or actually from 1 to 100 minus 50. So this is actually the kind of the time scale, so that we can time it somewhere at the middle. So this is the time or sampling times, actually, or sampling index. I kind of like the idea that the data starts at point 0, and then we can do our xxc, like xx causality test vector by multiplying xx dot times double ins greater than equal to 0. So, well, we are multiplying the signal with unit step function. There. So it looks like. Yep, looks like that. Actually, well, I made the same mistake as some of you. Okay, so it starts at 0. So now actually what we are expecting from the output is that it will be empty on the left hand side of that one. So there cannot be any data points before that 0. Okay, and same function. So let's see. No output before input, so we just run the test signal to the system and see what we have on outside. So output C equals filter. That's our 4-step running average. And then we have this test signal here. And check the first elements if they are 0. One way of checking it is, well, this is the easiest way. And of course it's, zeros. The first non-zero value is at 1. Okay, but anyways, the calculations, how to calculate if a vector is 0, well, we can always take, again, the norm of output C at the values index is less than 0. So that actually calculates the norm of the vector which is on the left hand side there before the 0 happens. That should be as close as 0 as it can. And yes, excellent, now we have exactly 0. So this system is also causal. Anyways, for time shifting, you may need to actually do some time shifting. So I'll just show you the time shift. So delay of 2 steps, for example, would be, I'll put it inside here, filter, or okay, and there you have, well, 10 steps, for example, like this. 1, 10, then comma 1. So this is a vector which has zeros on the beginning and then just 1 at the end, and then XXC. Yeah, it's the same test vector but delay of 10 data points. And then shift for advanced operation, meaning the plus something, you need that one on that one. I'll see if we have a reverse function. No, we don't have it.
I think you can use the flip.
Flip. Ah, yes, 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 flip, yes.
Flip step from the left
Flips.
to right.
Yeah, flip. It's just flip. Or
Or there's also the flip LR, so flip LR.
yes. Excellent. So yes, it's that one. Good. Thank you. So shift, the same thing. We flip the data and then we flip the data and we flip the output. Flip. So that's 10 time steps left. What would happen? Before I press here, what happens? What happens to the right hand side of the data? What will be the last 10 points? 0, of course. We generated only 100 points. Computer doesn't care. It just flips and moves data. If it doesn't have nothing to move, it actually just puts zeros there. So Matlab does it for you. So now if you basically would take a difference between this vector and the other one and see, oh, there's a big difference between these vectors, it would probably be because of that those extra points as an artifact came from Matlab. And with that warning, we go to the last one, which is the time shift invariance, since this is very typical when you're taking starting to do the time shift invariance kind of things, that okay, you will get, oh, this is not time shift invariant because of that. So you need to kind of be sure about your test vector and the output that you didn't cause that difference yourself. Okay, so those are the shifts, and that was the that example, and then time shift invariance means that the system should produce the same output as for delayed and non-delayed system. So basically, no, f y of n, then you should actually get the same as the if you have x of n minus k here, going through that one. Oh yeah. So fundamentally you should check if these are the same. Z minus k, there. So fundamentally, let's put it this way. One more way. Okay. Z2 minus k, going through that one. These two should be exactly the same. And time shifted, well, blah blah blah. Okay, these should be the same. We are testing that. So output for time shifted input should be the same as the output for, or time shifted output. Yes, that's the way. All right, and now we have still the system filter system, and we have already we have the time shifted. Okay, let's do some time shifting. So our test signal XSTS equals XX, oops, filter. Let's move it on time, for example at 10 time steps. Okay, like that one. Shifted input, and then we run this one to the output. F1 is filter. Okay. Right, output was shifted input, and then we have F2 would be the shifted output of the original signal. So we first calculated the this one here, F1, and then we calculated F2. Okay. Time shift, what is that point doing here, and then there, original signal, time filtered, and then this one time shifted. Yes. All right, and there we have the artifact. Since we time shifted a signal here, and I used the original one without these zeros on the beginning, I actually added some zeros to the data. So now the question is, are these the same? Maybe, maybe not. Well, I can actually, let's stem these. Does it go like this? Maybe. No. Ah. I need to use the plot, but anyways, that's the first one. Hey, they are the same. It's actually a good idea to actually do the both stem plots of those values and then calculate the norm. So norm, so the mean square difference of these two vectors. That's 0. Yes, they are exactly the same. So this might be a time shift invariant system. But for engineers it means it is time shift invariant system. If you want to prove it otherwise, use pen and paper. Good. So those are the tricks to use on the first 3 parts. Then I have to take a quick look on the exercise and to see. Ooh, wow. Excellent. Difference equation for the following system. Then zeros and poles, parameters, zeros and poles, and sound sample, and then filtering. Excellent. So, okay, that was the part A. Now the part B, which is system. Systems. Everything about the systems. So those are basically the tests to check if the system is what it's supposed to be. And then basically we go through the tool set to see what we can do with the systems. So basically just fundamentals. But okay, so let me start with the something that we already had here. We have the system. That 4-point running average. There we go. Y of n equals 1/4 of x of n plus x n minus 1 plus x n minus 2 plus x n minus 3, and there we already defined earlier when we were looking at the system parameters b and a. Okay, this is a0 equals 1. Then we have b0 to b3 are 1 or 4. So basically, well, if this was a vector, it would be something like this: 1, 1, 1, 1. We divide it by 4. Does it ring a bell? Okay, and this one has a couple of different ways you can show the implementation. So basically 1/4 times, then we have these delays, like that one. So this is the direct form system. On the exercise, I have given you this. You need to define, from that picture you need to define what are the system parameters. There's no magic actually on these. If you need to define the system difference equation on the system parameters based on this one, you can just do the brute force and just follow the signal. So here we have x n minus 1 on this point. If there's one delay, actually 1/4 times that one, and then we have 1.4 times x n minus 2. Oops. 1/4 times x n minus 3. So basically you can get the same equation also the other way around. So it's actually a little bit easier just to read. Let me take another view of this one. Just to read the signal from this drawing, determine what are the parameters on the difference equation, okay, which then turns into the filter coefficient or system coefficients at this point. Just a reminder about when you are taking of those feedback terms, this very easy to make the sign error. This one shows exactly how this yn actually should look like. Then you do the transfer function by moving the feedback terms in the other side of the equation, and that's where you usually make the small error on the sign. Okay, but with that warning, you should be able to avoid that. So basically, on that system, you would have a couple of terms here. Move it on the other side, then you will have A0, A1, A2. Okay. And in that order. And the one which matters here is actually, well, that is showing the scalar of that one. So keep the indexes the same. If there is some terms missing, then you will put 0 at the between. Okay, but that's quite straightforward example what we have there.
So if that's your, for example, if you want to use Matlab and you have those B0, 1, 2, and 3, but for example, in your running average there wasn't the number 3 at all,
Yeah,
number 2
the
at all, then
yes,
you have that
0,
because the Matlab
yes,
doesn't know otherwise.
exactly.
You are having more
Yes.
coefficients than just a few.
Yep.
But if some of them is 0, you have to put 0.
Yes, that's the idea. All right. So, but anyways, 4-point running average. So those are the. That's how I got on Matlab. On Matlab, I have this filter. Let's see, where do I have the filter command? For example, here are the F1 is filter 111. Oops. 111 divided by 4. So that's the running average filter coefficients for x. And then the other one, there's a scalar number 1 at the middle. Let me do that one over. This one. That's the parameters for y. If that was a vector, I would just put there a vector. But now I have a nice running average system. It has just that one number there, 1. B, A, X. Let's see. Doc. Filter. Yes. Output equals filter B, A, X. You just need to make sure that you are using those B's and A's the correct way, not the opposite way. All right. So that's the running average system, and then we need to do some, let's see, system, but okay, system parameters A and B, okay, with some warnings. Calculate zeros and poles. Alrighty then. We can actually show the zeros and poles of the system by simple command zplane. Okay, but anyways, first things first. So B equals 1 divided by 4. Actually, if we had a very long running average system, you shouldn't use that. So, but anyways, the same thing, you know, if you have very long, you probably don't want to use that many ones there. You will miss one in any case. So ones, whatever the number, the length vector divided by the number, that will give you those parameters. And for a equals 1, basically you could have also said 1 1 1 1 and then let the a actually be 4. For Matlab, it doesn't really care. It still does the calculus the same way. Okay, but this is following a kind of common convention. And then we can say the C-plane. Let's see if this one gives us the correct answer. I think this might actually give us a different answer. Wow, sorry, I have the hold on. Oh yes, it actually gives the correct answer, yes. Okay, so yeah, zeros, poles. Just a moment, I'll do some magic here. Looks a little bit better. Okay, so zeros on the unit circle. There's also a unit circle, real axis on the horizontal and imaginary axis on the vertical. Then we have triple pole at the origin. So that's how you mark zeros and poles. Okay, one warning: if I get any of those zeros and poles mixed, then it's you know, it means that you have messed up or mixed the a and b, the parameters. So one hint: I have this system there is a stable, meaning that the poles are inside of the unit circle, as they are, for example, here at the center of the unit circle. Okay, so that one already gives us information. Yes, this is also a stable system. So 4-point running average system is stable. Excellent. If you want to know the exact locations as a vector, so positions of zeros and poles, ZZ equals roots of BB. Okay, those are the points. 1 plus 0i, 0 plus 1i, 0 plus minus 1i. Okay, poles. Okay, now be careful, since this is an artifact that you generate yourself. How come? Well, it doesn't actually take into account that this is the fourth order polynomial coefficient. No, not fourth. Third order polynomial coefficient, as we did on pen and paper. So basically, the correct answer would be to add some extra zeros at the end. Since at the end, basically, you have the third order polynomial on both numerator and denominator, and that will give you the triple pole at 0. Okay, good. Let me take a quick look again. Zeros, poles, and stability. Determine, calculate zeros, poles, and then we have some sound sample and using the previous system. Okay, so the system implementation. If you have LTI system, that's filter BB AA XX, and we have already tried that one. So but now we have A and B, so let's see. y equals filter. I have defined b, a, then the input I have something like that. Oops, semicolon would be nice, but anyways, who cares? Stem ins, not x1 but y. Yeah, it looks like that. The original looks a little bit different. Let's check the that's the input. Output. Yep. You can see a couple of effects here. So amplitude is smaller. Why? Well, maybe because the running average is supposed to take off some of the randomness from the data. All right. So, okay. So that's concludes the this part of the this exercise. So now you have some time to start working on those exercises on your own. So first three fundamental properties: linearity, causality, time shift invariance. My advice is actually that you will generate some sort of functions you call from Matlab to do the tests. Then they are taking this plot and turning it into the difference equation to find out the system parameters, calculate zeros and poles, and check if the system is stable. Then take this system, calculate A and B, and zeros and poles. Then again generate a sound sample. Okay, here I have add random noise with amplitude, meaning this is directly the scaling term for the for that random number. Well, that would be the deviation, not quite the amplitude. But anyways, you just calculate, multiply your random numbers with this, and then the last one is actually to run your test signal through a filter and try to find out if how did actually it change the behavior, or how did the outputs differ. Okay, good. So I will be hanging around here until 4-ish. But anyways, that was my show. Thank you for listening.